Okay, let's get started. 我们开始吧。上次我们学习性几何，性几何和静电力学有很深层的一个关系。特别是一个 Hamiltonian system。So given the simplex manifold, 性有性 two-dimensional 性有性then given the function h is some smooth function 方法映射我们可以定义这个 Hamiltonian 下链场 Hamiltonian 下链场 xh by using the Simplicial form. So this is Simplicial form. 信息Simplicial form. Okay. And then using this Hamiltonian vector field, one can define a Poisson bracket like this. And in particular, is like this way. One can define commutator. So the commutator of Hamiltonian vector field, two Hamiltonian vector field, who give rise to the Hamiltonian vector field for Poisson bracket. So this can be shown by various way. And at the end of the last lecture, I briefly give an idea how to derive this last time. And moreover, so So given a Hamilton vector field H, XH, one can define so-called flow. So the XH will give rise to flow phi t. So one parameter pair become orthogonal. 同倍 flow. And then one can take a derivative with respect to the function with respect to this flow, which is given by the Poisson bracket between H and F. That's a Hamiltonian equation you are familiar with. In particular, if H if the function commute with the Poisson commute with the Hamiltonian H, this is the constant along flow. So this means that F is on the okay. Okay, so that's it. So for instance, the system has a spectral symmetry. Spectral symmetry. What is the conserved quantity? So Lagrangian or Hamiltonian. Hamiltonian with P squared n plus ER. It's independent of theta of phi. What is the conserved quantity? What is the conserved quantity? Okay, system has a translational symmetry. What is the conserved quantity? System has a translational symmetry. What is the conserved quantity? Momentum. Oh, good. Momentum. So if H can be something like that. So R to M omega. Okay. So omega is standard symplectic form, namely dp H dq. Okay. And for instance, system has a symmetry. Whatever A. So whatever translation symmetry. So translational symmetry, the conserved quantity Pi are conserved quantity. Okay. How about here? It's a spherical symmetry, rotational symmetry. What is the conserved quantity? Spherical symmetry is the system is independent of theta and phi. What is the conserved quantity? Yes, angular momentum. Then p theta, p phi, angular momentum. So angular momentum 角动量，角动量。Is conserve model. Okay. Okay, so that's how it works. So namely, so this computation between Hamiltonian and Hamiltonian and then but for instance, the f can be something like a theta in this case. Theta d dt. This is 0. So this means p theta is equal to 0. Up to some constant. The same thing. p phi is p phi dt. So those are conserved. That's why. Okay. So of course, I mean the h is independent of theta and phi. They call Poisson commute. Any question or comment? Okay. So now, sorry, before that, I have to mention, so the definition of complete, so 完全可记系统complete integral system. Integral system. Okay. So let's again, m omega, way 2n way 新流行 2n way 新流行 and then I1 to IN are C infinity of m such that they're all Poisson commute. And so there are the Poisson commute is called 互相对应，然后这个linearly independent. So which means that the di is not proportional to dij if I is not j. Okay. So they are linearly independent. Okay. Okay. So if this is the case, if there exists such a Hamiltonian function, so n function, if there is such n function, so this is m omega I, it's called complete 完全可记系统。So the maximum, so the z 的可对应函数个数条好位 n. Okay. So n is the maximum number for Poisson commutative function. So remember, so for instance, if you consider R to n and then omega standard, so the P1, Pn, Q1, Qn. Okay. If you have such a coordinate, so the Poisson commutative function is the z one, either z one or z one. Okay. Maximum number is n of Poisson commutative function. Pi, Pj, or Qi. But the Pi, Qj. Okay. So the maximum number of Poisson commutative function is up to n. But if there exists such a function, it's called completely integral system. And then I will review saying that suppose m omega I are complete integral system. Then so this I will give you M2 or S. Is there a function map? Okay. 惯化映射 Okay. 惯化映射 Okay. And then the theorem inverse of phi is as diffeomorphic to n torus, for p is Rn. Moreover, it's a Lagrangian. That's the theorem. I don't agree with it. It's a remarkable theorem. So, okay. So given the point B here, and consider pre-image of this map under this Poisson commuting Hamiltonian. So it's a pre-image, always isomorphic to n torus, and then it's moreover Lagrangian with respect to symplectic form. So that's the DB-Arnold theorem. And in particular, one can take the coordinate. In particular, so Tn is essentially S1, n of them, and then consider this one is the phi 1. So this is the phi 1 and the phi n are the coordinate of this S1. So it just S1 is just like this way. So it's just angle coordinate. Then omega can be written sum of di like this. And this I, phi I, are called angle action angle coordinate. Yeah, angle action coordinate. So 用中文说作用角坐标。作用角已经坐标。Okay, so that's the statement of I will leave it there. Okay. So therefore, if you use this so if you use so let me give you an example. Let's consider Hamiltonian, which is p squared of 2. So 写阵子 let's consider such a 写阵子 okay. 写阵子 then we can do the following Fourier transformation x like this. Okay. So if you do that, so you can just write down the dp which dx is the standard symbolic form of this Rn can be written as the di which d phi. Okay. Can be written like this. And moreover, so if you have a p and an x, so h is given by what? So if you plug this substitution into here, what would you get? Plug this one into here, what would you get? Sorry, I think I made a mistake. This is correct. What? I omega. One. Okay. I omega. Okay. So which means that the h is equal to constant means I is equal to constant. Okay. Hamiltonian is constant, which means that this is ellipsoid. H is constant is something like ellipsoid, like this way. And essentially, I is the like a radius, and theta is the angle. Theta is angle. Okay, angle point. So that's why it's called the 作用角坐标. And in particular, so if you solve the phi dot is equal to again h like this way, and this is equal to omega. I dot is equal to minus, and this is equal to what? H and I Poisson bracket between H and I is equal to what? 0. Of course, because H and I are proportional. it cannot be. So it cannot. They cannot commute. Okay. So therefore, so I is constant along the equation of motion, which means Hamiltonian is preserved. And energy. This means the energy conservation. Okay. And the phi dot is equal to angular momentum. That's what it means. Okay. So this is the energy conservation. And in particular, so if you do the integration between the phase space okay, and then we already knew that this is only depends on the one over two pi, and plug this p into here, and the x into here. What you get is that the square root 2i of omega 2i of omega like this way. Okay, and this is equal to I. Okay. So this means that the P dx means that so along this one you just integrate out all the phase space in here along the motion. So I equal to constant, h equal to constant motion is this ellipsoid. Okay, 椭圆. Okay, 椭圆. And if you integrate out, you get I. Okay, P dx is exactly you just measure this area, okay, and which can be integrated out. Okay. That's why it's called the complete integral system, because you can integrate out to get the area of the phase space. So complete integral system, you can do that. Any question? And in particular, so what's important is those ellipsoid are Lagrangian. So let's look at the statement. I don't leave it here. So statement. So here we have only one action Hamiltonian M to R, which is I, and its constant is it become S1. Okay. And you can easily see that this is S1, from diffeomorphic to S1. So this is pi inverse of I. Okay. Pi inverse of I. So I's constant is just this ellipsoid. Okay. So therefore, it's proportional to S1, diffeomorphic to S1. So that's the statement of the. That's a statement of the Arnold-Lewis theorem. So if you look at the constant part of the Hamiltonian or I, so it's isomorphic to, diffeomorphic to the S1. Okay, let me give you a bit more sophisticated example of the Arnold-Lewis theorem, because this is very deep theorem, in fact. So we写尖子 on the circle on the unit. Okay, suppose you have a periodic boundary condition. So you just connect these two, okay? So which means that you just have a circle, 写尖子 on the circle, and let's set m equal to 1. Each mass has a 1. Okay, so we consider such a system. Okay. And then how do you write the Hamiltonian? And then Hamiltonian can be written 1/2 sum of pi. So of course, each mass has a pi, the momentum pi and the coordinate qi. Okay. And pi squared. And then, so of course, Qn plus 1 is equal to Qi. Okay. Okay, so then, of course, the Hamiltonian equation is as before. So the Hamiltonian equation is as usual. Minus del h del qi, which is equal to omega squared and 2qi minus qi minus 1 minus qi plus 1. Okay. So that's what you get from the Hamiltonian equation. So we want to solve this Hamiltonian equation explicitly. Okay. So one can write down this Hamiltonian equation as follows. So suppose Q dot is equal to P dot and then P and P dot is equal to minus omega squared A Q. So now you just write down the Q as Q1, Qn, and the P as a P1. Like this one. And A is equal to, you can write that like this. So that's what you get. So 2 is, so diagonal 2 is coming from this 2. And minus 1 is just off diagonal entry. And it's periodic, so it has to be the end of the matrix should be minus 1. So that's the concise way of writing this Hamiltonian equation. Okay? Okay. How to solve this? How to solve this equation? How to solve this equation? Given this equation, how do you solve? So given this equation, how do you solve this equation? The thing you should do is diagonalize this matrix. Diagonalize. So you try to find a suitable base change so that you can diagonalize this matrix. Then it's easy to solve this the system of ordinary differential equation. So diagonalize this thing. And suppose that, and if you try to solve this so it's very easy to find the eigenvalue, and then it's very famous to do. I mean, it's very easy to find the basis, eigenvalue and eigenbasis, which is closely related to the Fourier transformation. So the diagonal A is equivalent to Fourier transformation. Okay. So suppose you have the A. So in diagonal A means as follows. So eigenvector is something like this one. Eigenvector x k is given by like this way. Like this way. Okay. So suppose xk is like this way, then x acts on xk is equal to I mean just simple calculation you can do. That if I'm suppressed, just give you answer ik over m of xk. So this is the so eigenvector and the eigenfunction. So it's very similar. So as you can see, this is already Fourier transformation. You will encounter those modes will appear in Fourier transformation. Okay. And in particular, so once you define capital Q, Qk is equal to square root m and sum of e to d. This is exactly Fourier transformation. Qi. pk is the same thing. So we do such a transformation. pj like this one, and then you can easily write down the Hamiltonian can be written as follows. The sum 1 over 2, sum of k is equal to minus 0 to n, sorry, 1 to n, such that the pk squared plus 2 omega squared, sum of k is equal to 1 to n, and the qk squared, and this yk over n. It become like this. So you do the Fourier transformation Q and P, okay? And then you define the suitable coordinate capital Q and capital P, okay? Then write down the Hamiltonian. So under which A is diagonalized, okay? So therefore, you can write down the Hamiltonian equation as follows: qk q dot k is of course pk, and here it's much nicer. It becomes just a minus 4 omega squared sine squared, and then qk times k. So it's now diagonalized. So therefore, you can easily solve this equation. Okay. So here is small pi dot is some bunch of coordinates involved, qk, qi. Whereas it's just here is k and qk, you just have this single coordinate. So you can easily solve this equation. And then if you solve it, so remember, so this is very important, and then how Fourier transformation should be. Fourier transformation should be taught in this way. So start with the couple harmonic oscillator on the ring, and write down Hamiltonian equation, and try to diagonalize it. Then suitable coordinate is the exactly Fourier transformation of Q and P. Okay, Q and P, such that they can the Hamiltonian equation diagonalize. Okay.
I have a question.
Yes.
In the last lecture, we talked about coordinates. Means locally we can find the coordinates. But I'm wondering that the completely global system, the definition of completely global system is just it seems like we can find the double coordinates globally. That. I mean, if we have
you mean omega is sum of di and wedge d phi? Is that what you mean?
Yeah, so it means we can find the double coordinates global.
So I'm gonna leave it here and say that if you have the Hamiltonian pi, good question. To n, as Rn, the pi inverse of B is the homology to n for generic B, in fact, generic B. However, for some special point, this no longer holds. Special point. In this example, special point is origin. So this point. Okay. This point is the pre-image of I equal to 0, Hamilton energy equal to 0, but it's no longer isomorphic to S1. So it just shrinks to the point. At this point, this coordinate doesn't work. So therefore, generically, this angle action coordinate will give you the double coordinate. However, some special point, it's no longer work. Yeah. Okay. Now you can solve this the owner linear differential equation. Maybe I can just write down the solution here. It's easy to solve. Then you have the QK of T e to the I omega k T and then this one and minus sign. Okay, so that's the case. Where omega k is of course is given by 2 omega by k, like this one. So that's the solution to this explicit solution of this system. Okay. And then the question is how do you find the Hamiltonian in this system? So Hamiltonian in this system. So to find Hamiltonian in this system is we just do the following what is the quantity in this system? So to see that, so we define AK is equal to square root 2 P minus K plus I omega K. Like this way. Okay. So here we just define a k is equal to plus minus 1 plus minus m, where the m is just a so capital N is, we suppose capital N is 2m plus 1. Okay. Suppose this capital N is off. So the things will be more transparent. So then what you get is that this Hamiltonian can be rewritten. Hamiltonian can be written. If you define like this way, Hamiltonian can be written like this way. It's very familiar form if you learn the quantum mechanics. Like this. It's very similar to harmonic oscillator. Okay. In quantum mechanics. Creation annihilation operator. Okay. And then so this is the case. So which can be easily seen from here. It's just pk. This can be written as just a pk square. Sorry, maybe here. So this is just a plus sum of qk square omega k square. Okay, omega k square. K equal to 1 k. Okay. So therefore, if you define AK and the AK bar, like this way, one can just write down the Hamiltonian like this. Okay. Okay, so suppose, and then, so Poisson bracket, as you can easily imagine, can be written as follows. Like this one. Okay, that's what you get. So you can easily compute this one. Then, if you do use this one, and it's suppose if you define like this one, ik, and this one quantity is I bar k, and it turns out that you can just, oh sorry, I minus k. Then one can show that so I0 dot is equal to 0, and then also ik dot is equal to 0, well, for any k. So these ik are the conserved quantity, as you can easily verify. So this one, these are really the conserved quantity, means the Hamiltonian. And in fact, one can show that one can show that each ik is a Poisson commute. When k for and k and that. Okay. So therefore ik are Hamiltonian. And this will give you a complete integral system. So this is the very, very like a higher dimensional version of the harmonic oscillator. So and then it contains the multiple number of Poisson commuting Hamiltonian. So this means that the system is completely integral system. So that you can solve exactly the system. Any question at this moment? Okay. So this is very, very like example. I think I really wish that all the physics students are familiar with. This is very nice system which involves the Fourier transformation, and also it's completely integral system, and then so if you and then its relation to the quantum harmonic oscillator. So for instance, for this kind of thing, so if you quantize it, you can have just a k, and then L is equal to some number times delta k. So if you quantize it. That's the creation annihilation operator in the quantum harmonic oscillator. Okay. Any question at this moment? Okay, so what we did is just start with the coupled harmonic oscillator, write down the Hamiltonian like this way, and then find the pseudo basis so that everything diagonalized. Everything diagonalized. In any case, Hamiltonian can be written as the so essentially one half, and then omega k, omega 1, omega n, and then q and capital P and capital Q, and then so that's the Hamiltonian is really diagonalized. P and Q. If you write down if you use a Fourier transformation, you can just really diagonalize it, and then one can solve the equation of motion. In that system, you can define the conserved quantity. So then conserved quantity, and you can have the action point. So that's what happened. Okay, so this is the end of the simplectic geometry. Any questions? Okay. Okay, so we will move on. So move on to topology. So now, so far呢，至今我们学习依赖的是光化结果的微分几何，但是现在OK。本讲进入代序拓扑的代序拓扑就是 topology。So 代序拓扑只需要拓扑空间结构 ，so continuous map， so 变数映射。No need to be smooth. No need to be smooth. So 不需要的是靠微心。Okay. So this algebraic topology initiated by Poincare in the beginning of 20th century, around the 1900. Okay. In particular, so we already learned something like a drum called homology. Drum called homology is defined by the B 形式. So B 形式 quotient by 恰当形式 exact form 形式 And then we will define a similar thing in the following. So we will define so-called homology. So 同调群. In particular, so in this lecture, so we will consider Simplicial. Simplicial 单群同调 Simplicial homology. And we can define as a dual group as a cohomology. Okay, cohomology group. Moreover, we will define a fundamental group. So fundamental group is 基本群. Here it can be some ring R or HK. However, and so on. So that's what we are going to learn from now. Okay, so that's so in algebraic topology we don't need this 光化型. We just need a continuous 连续型. Okay. So now, we will define a homology group. And call homology. First, we will define a homology group. 同调群. Then 定义同调群. Well, now, 结效的是同调群，我们考虑的是单群型 simplex. So simplex, we will consider simplex. I have to say that so the reason why I call it the Simplicial is that there's another version which is called singular homology. Singular homology. Which singular homology? Singular homology is when you consider the modern algebraic topology, singular homology is suitable, but it's almost impossible to do the computation. Unless you use some kind of exact sequence and so on, which I will introduce from now on. But the Simplicial is like kind of old-fashioned, but it's more intuitive. So I will explain that the Simplicial homology rather than singular. Singular homology, if you're interested, there are many books, like for instance, like Hatcher. So the very, very Hatcher's book is available online, which is very, very, authentic, like I would say, like a very treat algebraic topology very, it's a standard book in algebraic topology, one of the standard books in algebraic topology. But instead, we considered it a Simplicial homology. Okay. Okay, so the Q simplex. So simplex, Q simplex. The definition is the, you just consider A0 such that, so this is the Q plus 1, a finally independent general coefficient points in Rn, and then you just define. For instance, if you have the so these are the simplex. This is the two simplex. Okay, such that the sigma okay, so that's the key. So for instance, yeah, in this is two simplex. Okay. And then sometimes called T0 to TQ is called barycentric coordinate. 我不知道用中文怎么说 barycentric coordinate. It's called 重心坐标。重心坐标。And in particular, okay, and also, this is Q equal to 2, Q equal to 0, Q equal to 1 is just line. Q equal to 1 is line, and Q equal to 3 is something like this one. Something like this. Okay. And the boundary of this one. So one can what's the boundary of this one? The boundary of this one is still exactly. For instance, boundary of this one is something like this one. Okay. So this purple part is boundary of sigma. Boundary of sigma is this one and this one. Okay. Here, when Q equals to 3 case, you also consider the interior of this 四面体. Okay, it's cone, so interior, but the boundary is really the faces of this, like these four faces in the for this three simplex. Okay. Okay. And then when we group these simplex together, these simplices together to build a complex, so then we will define so-called and then we define a so-called Simplicial complex. Complex is the we glue them together. So we just glue them together to create the Simplicial complex. So for instance, is a defined as follows. This is 单群 sorry. This is 单群复兴。单群复兴 is defined as follows. Okay. So if sigma k, let's go k. Sigma inside k, then and those faces is called tau is sigma. Okay. So for instance, A0, A1 is inside the A0, A1, A2. We use this notation to show that these are contained inside the faces of this simplex. If this is the case, tau of sigma faces also tau is inside K. Number one. Number two is that the sigma tau is either empty or is either empty or faces of sigma empty. Okay, so that's the case. So let me introduce. So for instance, if you just consider the following thing, so the Simplicial complex is something like this one. So those suppose we have such a face. This is two simplex, and then here you have the whatever. These are three simplex, and this is one simplex. These are the Simplicial complex. However, if you consider the following thing, if you consider the following thing, this is not the simplex. For instance, if you consider sigma here and tau here, okay, tau here, and then here, this part is sigma union tau. Okay? This is a face for tau. Okay. However, this part is not face for sigma. Okay. The face for sigma is something like this one. Face of sigma is this red part, but this green part is not clearly not the face of sigma. So therefore, it doesn't satisfy second condition. Okay. Second condition， 不满足第二的程序。所以这个不是 单纯不幸，复性，复形，这个不是意思。对。OK，And also, so this Q skeleton of K. Q skeleton K is just all the sigma in K such that the all the dimension of sigma is less than Q. So that's the case. For instance, in this example, one skeleton is like this one. This one and this one, this one and this one, this one, this one, this one, this one, and this one. These are one skeleton. And two skeletons is these faces and so on, including this red one. Okay. So those are skeletons. Two skeletons. 骨架 ，no， 骨架 Q 骨架 Okay. And in particular, so if you just write down this, this one is just if you write down this one, here it's just entire set. Entire set. Set of points in K. So that's Q bar. So K then like underlying space. So this is the underlying space of K. And then so we consider so-called triangulation. Triangulation of the some space. So triangulation. So triangulation is the such a what? How to say in Chinese? Oh, triangulation is 三角部分 No, 部分 Okay, 三角部分 So such a bullpen of the so topological space M. So did I call it M? Yeah, triangulation space of M. So M is a topological space, and triangulation is exactly the homomorphism. Okay. M. This is the homomorphism. This homomorphism. So 这个同配。Okay. It's called homomorphism. 同配，yeah, 同配。For instance. Let's consider an example. Okay. So the example, the S1 is the S1 is, this is also, okay. Okay, so this is also triangulation. S2 is something like this one. This one is also triangulation. Of course, here the inside is not included. Okay, this is triangulation, but not unique. There are many triangulation one can consider. This is also another way of do the triangulation for S2. How about T2? T2 triangulation. This is also triangulation torus. Okay. Triangulation torus. And so on. Okay. And by the way, so I just write down this is denoted by K scalar denoted by J is denoted by KD. KQ. Sorry. KQ. Okay. So this is a triangulation of the space. So as you can easily see here, we don't care about it's smooth or not in this triangulation. We just care about the continuous or not. We don't care about the wave function. Okay. And then we will define a chain group of K. Oh, yeah, sorry. And then we need to talk about this Q simplex. And also you can consider oriented Q simplex. Oriented Q simplex. So in this case, this is the 定向 或有向定向的定向单纯型。So we just consider it with ordering. So we care about the ordering, and so therefore, if you change the ordering, so you need to include sign of sigma a sigma 0 a sigma q. Sigma is a permutation. Namely, so if you consider oriented as 0, so in this example, A0, A1, A2, suppose this is the orientation, which means that the orientation is something like this one. A0, A1, A2, orientation like this one. So you can also write down A1, A2, A0, or minus A0, A2, A1. So you can just, including orientation, we can define oriented Q simplex. 定向. Okay. Okay. And then we define so-called chain group. Chain group is chain group is the 连复型 U. Okay, so then we define so 连复型 chain group. So I will explain why it's called 连复型. Chain group Q 连群 连群 Q 连群. Oh, it's hard to write. Oh my goodness. 链群 Q 链群. So suppose the let's consider K is the Simplicial complex. This Simplicial complex is really oxymoron. So you just each piece is Simplicial, but you just combine them together. You just call complex. Simplicial complex and the sigma 1 to the sigma L are the inside a Q skeleton. Q simplex, and then of course with orientation. Okay. Then CQ. Yeah, sorry, this is Q simplex. So is it the right thing to do? Sorry. Yeah, the KQ is the span. Span K of Q. Then C of KQ is equal to so abelian group. This is abelian group. It's abelian group. So isomorphic to this is L. Okay. That's the case. And then we define so-called boundary operator. So boundary operator is something like a 边界算子. The boundary operator CQ of K to CQ minus 1 of K. It's a linear map. It's a linear map such that the boundary of Q of sigma is equal to the boundary of Q of A0, AQ is equal to sum of minus 1 to the I, A0, AI, AQ. I is equal to 1 to N. Sorry, Q. Okay. So that's the case. So this, hat is just omit. So omit. So that's 边界算子的定义。So let's consider this example. So if you consider the boundary of A0, A1, A2, which is equal to, let's do that as a definition, A1, A2. So just get rid of A0 first. The next is the remove A1. Okay, remove A1 means the minus A0, A2 plus A0, A1. Okay, so that's it. And this is equal to A1, A2 plus A2, A0, and then A0, A1. Okay. So if you do that everything cyclic, it becomes plus sign. Whereas here, so you just consider orientation. So without it. So that's the case. 2 to 1 sentence. And then you just consider point thing. The maximum dimension of the K is something like this one. N, you can have following map. So the boundary operator and boundary operator, boundary operator, boundary operator, like this way. Okay. So this is called chain complex. This is called 衍复型. This is called chain complex. So the reason why it's called chain is that this diagram looks like a chain. Okay. It's like a chain. 连. So this diagram, it looks like a chain. So that's why it's called chain complex. Okay. And from there, so I think it's a good time to stop. We will construct. So we will show that the delta square equal to 0. Delta square is equal to 0. So this is equivalent to the dynamical homology with sort of d square equal to 0. Dynamical homology. So therefore, we can define so-called exact or closed and so on, and then we can define a homology. Okay, let's stop here and take a break. The simplex. Sigma is the simplex. Q simplex. Q simplex. Or simplices.
squared function up there, or is insider definition, or it's just a proposition?
Proposition.
Proposition.
So if you use this one again, it should
Okay. But in the textbook, it just looks like it's inside. It looks like it's inside the definition.
Yeah, I told you we can show
Okay.
the square definition.
So what do you mean by sigma 1 to sigma x? Can you say the vertices?
But for instance, in this example, the span K1 is, so this is the sigma 1, sigma 2, sigma 3, sigma 4. So these are span sigma 1 and K1. One sigma.
Okay. So, yes.
Sigma 1, sigma 2, span the K2.
So they have to be the same dimension.
Yes. 那我们继续。我们继续two students more. Okay, few moments here. I forgot to mention one thing in the那我们继续吧。So 我们导印这个辩护型然后这个边界算子边界算子的形距是这个 boundary square is equal to 0。这个可以确认这样的。So boundary of these two simplex is this one， 是这个。然后 boundary square，if you apply boundary square， 我选上去。Boundary, if you apply further boundary or more, then we'll make okay. Okay, you can just apply it. So just apply 应用这个边界算子。To this complex function, you get the A1 minus A2, A2 minus A0, A0 minus A1. And of course they cancel, and they cancel. They equal to 0. Likewise, the even higher dimensional simplex, if you apply the boundary operator, one can just obtain the boundary square is equal to 0. Okay. So it's very similar to what we saw in the manifold. So if you have a manifold, and if you have a boundary, so this is the manifold M, this is the boundary of M, but the boundary of boundary is equal to nothing, empty. Okay. Boundary of boundary is empty, in fact. Okay. So therefore, it's very similar to what we saw in the. Okay. So we can confirm that the boundary square is equal to 0. So this means that the if you consider by the way, so this is a homomorphism. Okay. The homomorphism Yeah, homomorphism in the sense that if you apply, so this is the abelian group. So it's spanned by z sigma 1 z times sigma l. So now for the element of this one can be written some n l and I sigma I is equal to 1 to l, where n I is equal to is the some z. Okay, and if you apply boundary operator, this is the homomorphism. So therefore, I like this way. Oh, sorry. You cannot. Okay, so like this way. So boundary, if you apply this one, so you can just factor through this coefficient and you just apply to the simplex itself. Okay. So each simplex. Okay. And then, so the one student asked what the meaning of sigma 1, sigma l, sigma l spans the KQ. So for instance, so in this example, one skeleton is spanned by this sigma 1, sigma 2, sigma 3, sigma 4. So in this example, two skeleton is spanned by this sigma 1, this sigma 1, and then this sigma 2. And in this example, two skeleton is spanned by here. Sigma 1, sigma 2, and then sigma 3, and sigma 4. 四面体，所以the four faces, those are two spanned by two circles. Okay. So therefore, so the boundaries, so these are abelian group, you know abelian, meaning abelian group, right? It's a group that can commute. Okay. Abelian group. So in general, it can be any like a ring. So it can be like so more precisely, this one can be just written like this one, and then it can be Q, or it can be C. R. It can be C. It can be C, or some any ring is okay. Okay. More generally, it's just it's a ring R module. It's called R module. But I'm not going to go into detail or what the meaning of R module means. Anyway, R is a ring and the module. But I'm not going to explain what the meaning of R module. So you have an abelian group and the abelian group. So boundary operator set like this way. So this is image of boundary operator. And then next you look at like this way. And this is a kernel. This is a kernel of boundary operator. So therefore, kernel of boundary always contain the image of always contain because of the boundary scale is equal to 0. Okay. So always, I mean, image of a boundary is contained in the kernel boundary because of this condition. And of course, the as in Gram Shank, so we will define the difference between Gram homology and then this wide range differential form 外信息 and then this 链复性是dynamical homology. The degree is increasing the opposite way. So here degree is decreasing, right? So if you take a boundary, the dimension will decrease by 1. But for dynamical homology, the arrow is the opposite way. But the mechanism is the same. The kernel of boundary contains the image of boundary. So therefore, we can define the Simplicial homology. 单群同调群的定义是HQ of K of Z is the like this one. So in this example, the difference between these two is around here. So this difference between kernel and the image is HQ, H of K. So that's the definition. the 单群统调群的定义。Now let's do the computation, maybe. Let's do the computation. So let's do the computation. So let's do the computation for this one. So the simplest example is S1. Okay. Let's go through this one. So the C1. Oh gosh. The joke here is not good. C1 of this K is C sigma 1 and C sigma 2 plus C sigma 3 plus C sigma 4. Okay? What is the kernel? So the kernel of boundary 1 is equal to what? What is the kernel of boundary 1 for this one, the example? What is the kernel of this boundary map? Sigma is oriented, of course. So Z, sigma 1 plus sigma 2 plus sigma 3 plus sigma 4. Okay. So that's the kernel. Okay. We have A0, A1, A2, A3. Okay. And then if you do that, it exactly the same mechanism. A1, A2, A2, A0, A0, A1. If you take a boundary operator, you get 0, right? You get 0. It's the same mechanism here. So we just applied 0, 1, plus 1, 2, 2, 3, 3, 0. Okay. Then if you apply boundary operators, so this is 0 minus 1 plus 1 minus 2 and so on. And you cancel and cancel and cancel and cancel, you get 0. Okay. And this chain compass is the C1K, C0K, and D. And this is the, so therefore this one is the H1. And then this one is H1K. H1K. Okay. How about C0? C0 is the C0 of K like this way, 4 dimension. What is the kernel of
C0.
C0 itself?
Yeah, because kernel.
Sure. Okay. This is C0 itself, in fact. Because boundary with A0 is just empty. C0 itself. The question is, what is the image? C0. Image of is Z a 3-dimensional. If you add one more, A3 minus A1, but they are linearly dependent. But if you then add them up, you get 0, right? So you cannot add that A3 minus A0 because they are linearly dependent. Okay? So it's a 3-dimensional. So this is the D4, D04. Okay? If you take quotient, you get the H0 of K with kernel of boundary 0, image of boundary 0, which is as more to Z. Okay. Okay. So this means that you can pick any point. You can pick any point. So you have a 4 representatives of this H1. You can pick any point. You can pick A0, but that is equivalent to A1 because of this relation. A0 minus A1. It's just quotient by image. So therefore, this means that A0 is A1, is A2, and A3. As an inside homology group, 0-dimensional. Do you understand what I mean? Okay. So in general, zeroth homology group of the Simplicial is the Z times number of connected component. Number of connected component. H0. So in this case, connected component, only one connected component. Okay. In this example, so therefore, the H0 is Z, just 1, Z to 1. Okay. But if you have 2 connected components, you have Z square, Z4, and so on. So the summary is that the summary is that H star, HK of S1, C is HK of, what was that? K of C is Z, when K is equal to 0, 1, otherwise 0. Okay, so that's what it is. Any question at this moment? Do you want another example? Shall we do another example? Okay, let's do that a little bit slowly. Let's do this example. This example. Torus, two torus. Example 2. E2. Okay. So yeah, I just had it twice. So you have only one vertex. Okay. Let's call it sigma 1, sigma 1, sigma 2, sigma 2, maybe upper 1, upper 1, upper 1, upper 1. Starting for one simplex. Let's go tau 2, 1, then tau 2, 2. What? Oh, thank you. So let's go this way. Let's go this one is sigma 3, 1. And the orientation is something like this one. Always orientation is taken like this one. Okay, that's orientation. So this means that the if you take a boundary, so you have a this one and this one and this one like this one. And here you have a this one, this one, this one. Okay. Okay. Then suppose we take the orientation of this one is something like this one, maybe. Okay, maybe use the sigma 3 orientations. Okay, so what is the kernel boundary 2? What's that? Okay, C2 of K is C tau 2 tau 1 plus C tau 2 2. Okay, let's remove now 1 and 2. It's redundant. How? What is the kernel of the boundary 2? This one. 8. let's look at the example. Boundary tau 1 is sigma 1 minus sigma 2, because I take this way of orientation, and then minus sigma 3. Okay? If you take like this way. Boundary tau 2 is with minus sigma 1 plus sigma 2 plus sigma 3. If you sum them up, you get 0. In general, compact, the top form of the K. So M is, okay, K, dimension K is n-dimensional, and this one is the compact, closed Simplicial complex. Namely, so K to M, this is a triangulation, this guy is closed manifold. HK of M, Hn of Z is the Z which spanned by entire M, or I would say entire K. I mean, okay. I don't know how to write. Yeah, Kn, something like this one. Yeah. And this is called fundamental class. G density. Most likely. I just guessing. Class. Okay. Closed, most oriented manifold. Oriented. Fine. And then since this is the H2 of K. What's H1? Kernel of the one is the everything. C1, okay? That's obvious. Because I mean, if you take a boundary, all the points are same. So A0 minus A0. The image of 2. Image of 2 is this guy. Z boundary tau 1, Z boundary of tau 2. Okay? Z boundary. So this guy is Z3. Okay? Equals sigma 1, sigma 2, sigma 3, right? Z3. Oh, sorry. So, sorry, this one is dependent of this one, so you cannot have this one. Okay? Is it okay? Therefore, if you take the H1 of K is kernel of boundary 1, image of boundary 2, which is isomorphic to Z. Okay? Square. And then if you be careful about if you try to be careful about this, the most natural way of taking is Z sigma 1 and plus Z sigma 2. Z sigma 2. So sigma 1 and sigma 2 are the okay. But you cannot add sigma 3 because of this relation. This is equal to 0. Okay. Sigma 3?
1 and 3.
Is also okay. Also okay. But that's true. That's true. That's true. But yeah. This is exactly what happened if you consider sigma 1 is something like this one, sigma 1, S1 here, and then sigma 2 is this 1. And the same reason, H0 of K is of course Z, A0. Okay? So this is A0. Because even if you, okay, so image of sigma 1 is equal to what? 0. Good. Because in any boundary of the edges, A0 minus A0, you get 0. Therefore, it's just a H0 is this. Fine. So summary. Like this. That's fine. Let's try to do a bit more example. It's kind of fun to do the example. Looking at definition is boring. So if you have the definition, you have to work with the example. RP2. How to do the triangulation or RP2? What's the best way to do triangulation RP2?三角剖开，三角剖开 ，RP2 的三角剖开怎么做？剖开，三角剖开，三角剖开。This is the best way. You understand what I mean? Or maybe it's better to looking at it this way. And then you identify like this way, this way, this way, this way, and this way, this way. Do you understand what I mean? So here A0, A1, A0, A1. Do you understand what I mean? Do you understand?
P1.
No. So the sphere, and you just identify opposite point, right? And then here you just get rid of it. And then this northern hemisphere is the interior of this square. Okay. But this boundary, you have to identify this. So this part and the opposite part. And this part is exactly this part. That's all right. Is it okay? Are you with me? So this northern hemisphere part is this part, in period. And the boundary, so you just identify this one and the opposite part is exactly fine. And again, to do the same thing, tau 1, tau 2. And I call this is sigma 1 and sigma 2 and sigma 3. And then let's do this. Okay. What is kernel of sigma 2? Tau 2. What is kernel? And maybe, I don't know, would you look at orientation something like this one? And then we take orientation of tau 1 as like this way. What is the kernel of tau 2? Exactly. It's empty. Let's look at tau 1 is sigma 3 minus sigma 1 minus sigma 2. And 2 is equal to minus sigma 3 minus sigma 1 minus sigma 2. Okay. There's no way to get 0. So it's empty. So therefore, so 0. So this is very typical for unoriented, non-oriented, or unorientable surface. Next, kernel of tau 1 is super easy. The kernel tau 1. Okay, so what's the kernel tau 1? Okay. Is it okay? Or, yeah, sigma 1, sigma plus sigma 2, or it's easy. Okay. Is it okay? If you take a that boundary A0 minus, always A0 minus A0, both sides. However, there's an image of this guy. So that will identify sigma 1 plus sigma 2 is sigma 3. Okay. This is equal to 0 or plus minus. So therefore, so H1 of K is the whatever sigma 1 plus sigma 2. Maybe? Is this correct? Or not? You have to be careful. Let's do that. Let's do it very carefully. Okay? What is the image of boundary 1? Boundary 2. This is C sigma 1 plus sigma, okay, anyway, Z boundary tau 1 plus Z boundary of tau 2. And what is the H2, RP2, Z? Okay. From here, it's clear sigma 1 plus sigma 2 can be identified as sigma 3. Okay. But plug that one into here. Okay. So this means that the plug that one into here, then okay, so let's do that. So sigma 3 is identified as sigma 1 plus sigma 2 by this relation, because this is equal to 0. Okay? But now plug that one into here. Then this is equal to 0, meaning that the 2 times sigma 3 is the 0. Do you understand what I mean? So plug this one into here, you get the minus 2 sigma 3 is equal to 0. Okay. This means that you cannot write down this one is sigma 3. Because 2 times sigma 3 is 0. Do you understand? C2. You understand? But it's natural, because, see, so the boundary of this northern hemisphere is 2 times, this is sigma 3, or sigma 1 plus 3, sigma 2. 2 times sigma 1 plus sigma 2. The boundary of northern hemisphere is just equator, so that is 2 times sigma 1 plus sigma 2. That is trivial. So generator of the H1 is this orange one. But if you multiply 2, you get that you can just shrink to that. So if you just have a, this is 2 times sigma 1 plus sigma 2, but that can just shrink. I would call it, this is homotopy, to the point. This is the point. I would say what's the meaning of homotopy? Homotopy. So you just shrink to the orange. So this means that this H2 is Z2. Okay. And then the H0 is super easy. It's connected, as I mentioned, it's a connected component of RP2. C is C. Either one is okay. A0 or A1. A0 or A1. Which one is okay? Everything is okay. The summary. HK of so that's the homology, Simplicial homology of RP2. Okay. Any question at this moment? Fine. Now, so we define the Simplicial homology group. Then we'll move on to the something like how it behave, and okay. Okay, so bunch of things I have to explain. So after E, bunch of things I have to explain. So the first of all, so bunch of things I have to explain. First of all, so I will explain later. So, but if you have two triangulation, phi is k to m, phi prime is k prime to m. We can show HQ of k z is isomorphic to HQ k prime of z. So it's independent of triangulation, in fact. So you have a, for instance, for circle, you have a triangulation like this way or this way. So S1, two type of triangulation, but it's independent of how you do the triangulation. So that I will explain briefly later. Another thing, so this is more like this is something related to topological invariant. Yeah, so I will explain. So by using the homotopy invariant, I will explain what the homotopy means. And then, moreover, so the order characteristic of M for this compact or closed manifold, maybe compact is better, whichever is the case. Manifold M, this can be defined as a manifold to the I dimension of Hi of M R. So this is very important. I is equal to 1 to M. Or I is greater than. So here, very important to the R. So this is important to the R. Or if you want this one, this is definition. Or sum of I is greater than 0 equal to 0 minus 1 to I. So only take the Z part of the homology group. This means that so for instance, we already knew RP. What did I erase? Somehow I erased. So this means that, so we already know that the HK, oh, did I erase? RP2 homology group, I already erased somehow. Okay, somehow I stupidly erased. So RP. Like this way. So in this case, only you just count the dimension Z, not Z2. So therefore, order characteristic of RP2 is equal to what? What? Say it again. So you just only count the dimension of Z. So here, 0th degree, or maybe I is better, or anyway, K, or I is better, or anyway. 0th degree, you just contribute. Dimension Z is 1. Okay. So therefore, you get the 1, but the other you don't get any contribution because I mean dimension Z of Z2 is 0. Therefore, this is equal to 1. Okay. Just oral calculus RP2 is equal to 1. Okay, to compute H1 of RP2, R is the homework, so I'm not going to say anything. Okay. Bunch of things. So now we define the H1, Hi of K of ring R. So then we want to understand how it behaves on the map of like this way, or what is the invariance, amount of invariance. And also the property. So we need to consider property of this one. So how it behaves under the map. How it behaves, what is the homology invariance, and how to compute. So that's a question we will have. Okay, so that's a question we will ask. That's a very natural question, and we need to answer this question. Okay, so the Simplicial map. So to understand the first one, we need to understand the Simplicial map. Definition. Simplicial map. Definition is that the given a simplex this is also simplex of K prime. Okay. So for instance, if you have this one, A1, A2, A3, A4. If you map this one, is something like FA1, FA3, FA2, FA4. So if the triangle shrinks to this line, it's okay. But you cannot define something like a in principle this can be done. You cannot map this one to be something like this one. FA3, FA2, FA3 is equal to FA4. Okay. So if you look at this one, so this triangle is mapped to these two lines, two simplex. Okay. this triangle, this two simplexes map to these two lines, these two simplex. So that's not allowed. So this is not Simplicial map. Okay, and we will say about something about how this F induces at the level of homology group. Next lecture. Let's talk. Okay. Ayo. Yes.
Here's the dimension of C2 over 0.
Yeah, dimension.
Because you cannot find a generator.
Yeah. Yeah.
Okay, so for vector spaces, we also have maybe this is the definition of
DMC.
DMC is over Z module or Z module.
Yeah, Z module has to be like a Z to some power.
Yeah. So
You just call them
if
many
you
components.
if you consider a vector space, it's a R module, a real vector space. So can we find an example? It's not zero vector space, but it also has dimension equals to 0. This is an example.
Like a Z sub n or something like that.
Yeah. And you have this one, right?
Yeah.
But can you find something is equal to 0, but this is not 0 vector space.
No, you cannot.
You cannot. Okay.
Because R is a field.
R is a field.